average velocity and average speed, now in two dimensions. Back in 1D, the average velocity we defined as being your displacement over time. Displacement was a scalar, so average velocity was a scalar, as is everything in one dimension. In two dimensions, though, our displacement we know is now a vector, so our average velocity is going to be a vector too. It's going to be a little more complicated to define. Average speed, however, is going to be exactly the same in 2D as it was in 1D. That was just the distance you traveled over the time that it took. So in two dimensions here, if we're starting at this position, moving along this path to our ending position, then the distance traveled is just this total distance added up here. All these steps along your path make up the distance traveled. And that divided by the time it takes will give you the average speed. That's simple. Now, for your average velocity, we need to know your displacement. Here's where you started, here's where you ended, so we can draw in our displacement vector, an arrow pointing straight from your initial point to the final point. And that is the change in our position, which is a vector. There's our displacement vector. Our average velocity is going to be a vector parallel to this one. It's pointing from our initial point to our final point. Our average velocity is the velocity we would have if we had moved along that straight line path from point A to point B. So our average velocity will be a vector parallel to our displacement. Average velocity and then the harpoon symbol to show that it's a vector here. Our definition then, the average velocity is our displacement over time, but this is a vector, so this is a vector. And it's going to be parallel to the displacement. So here, if we've got some examples of different displacements from point A to point B, our average velocity would be parallel to it from point A to point B, velocity, point A to point B, average velocity each time. Okay, let's look at this in more detail. We can't really use this equation as it is because it's in terms of vectors. We're going to have to separate it into components in order to use it. So our average velocity here we could break up into components by making the arrow the hypotenuse of a right triangle. And this side is our x component of the average velocity, comma x, the x component, and that is just what's familiar from 1D, the change in x position over the change in time. Likewise, the vertical component here, that we'll call the y component of the average velocity, v average, comma y, that is the change in your y position over the change in time. So when we're talking about velocity in 2D, we have a component that's the rate of change of x and the rate of change of y. Okay, I've got a problem for you to work out. Let's put some numbers to this scenario right here. Let's say our initial position is 2 meters, comma 5 meters, and our final position is 8 meters, comma 1 meters. So here's our initial position, here's our final position. Let's say we traveled along this path, and I'll tell you that the length of that path, d, will be 11 meters, and the total time of the trip will be 9 seconds. So with that information, for this trip, can you find all of the following? Delta x and delta y, use those to get the magnitude of the displacement and the direction of the displacement vector. Then find the x component of the average velocity, the y component of the average velocity, use those to get the magnitude of the average velocity and the direction of the average velocity, and lastly, find the average speed. Pause the video, work those out. Ready? Here are the results. Delta x, delta y, and the magnitude, pretty straightforward. When finding the direction here of your displacement vector, even though our displacement vector wasn't coming out of the origin on our map, when we want to find the angle, we're going to redraw a little set of x, y axes just as if the displacement vector were coming out of that origin. This is sort of a private set of xy axes just for this vector. And we use it to find the angle relative to the x-axis here. We pick the x-axis angle because the vector is closer to that axis than it is to the y-axis. So our delta y over delta x, that is the negative 4 over 6, gives us an angle of 34 degrees right there. Looking back at the picture, we see that our displacement is down in this direction. So if we sort of translate that to the x-axis here, we are 34 degrees below the x-axis here. That's the direction of our displacement. Okay, and then looking at the components of the velocity, of the average velocity, the x component, the y component, then add them using Pythagorean theorem to find the magnitude of the average velocity. Same thing to find the angle here. We're going to redraw the average velocity vector as if it were coming out of the origin of its own little personal xy axes here. These are the legs of the triangle. Tangent of that theta is delta y over delta t over delta x over delta t. This divided by this, well, we're dividing a fraction by a fraction. So that's like multiplying by the reciprocal. So I'm going to take delta y over delta t times the reciprocal of this, which would be delta t over delta x. Those delta t's cancel out. So tangent to y over delta x, just like it was up here. So this came out to be an angle of 34 degrees. This, of course, will also come out to be an angle of 34 degrees. So our average velocity is also 34 degrees below the x-axis, parallel to the displacement as we expected, parallel to the displacement vector. We proved that those two angles are the same. And then lastly, the average speed is straightforward. That's just the distance over the time. Oh yeah, notice the average speed, compare 1.2 meters per second to the magnitude of the average velocity, 0.8 meters per second. Average speed is larger than the magnitude of the average velocity. That's because, of course, this distance traveled, 11 meters, is much greater than the straight line distance, 7.2 meters, the magnitude of the displacement. That 11 meters is greater than the 7.2, so your average speed comes out to be greater than the magnitude of the average velocity. That's always the case.